Good morning, everyone. In this video, I'm going to go through 8.2, which is integration by parts. We're actually done with chapter 6 now, so we're moving back to integration techniques. And integration by parts is the first new integration technique we've seen since U substitution. If you remember, U substitution is sort of the integration version of the derivative rule, the chain rule. Since U substitution deals with an inside function and kind of what extra pieces would come from that so we can adjust for them going backwards. Integration by parts is related to the product rule. So we typically use integration by parts on integrals of products of things, although there are some exceptions that we will see later. So the derivation of this actually begins with the product rule. So I have the product rule written out here. We've got the derivative of u times v is equal to u times the derivative of v plus v times the derivative of u. And I want to just integrate both sides of this with respect to x. Now on the left-hand side, since I'm integrating the derivative, this will just cancel and I have u times v. On the right-hand side, I get two integrals. I have the integral of u times, now I have a derivative of v times a dx. And if you put those together, you actually get the differential dv. So remember, this is really the derivative of v with a dx. Plus, then we're going to have another integral that's v times the derivative of u times dx, which would be a du. Okay, and I'm just going to rearrange this a little bit. I'm going to subtract this one to the other side. And we get the integration by parts formula, except that it's actually backwards, so I'm going to flip sides as well. So the integration by parts formula says the integral of u dv equals u times v minus the integral of v du. So this is a way to turn this integral, this is sort of our starting integral, into a difference between two things, with the idea that this new integral will hopefully be easier to integrate. Alright, so here's our form again. This is the mnemonic that at least I learned for integration by parts. So when we do the integral of u dv, we get uv, which is ultraviolet, minus super voodoo, so that's the super means the integral sign, and then the v du. So when we apply integration by parts, the first thing we have to do is figure out identifying the parts u and dv in the original integral. So I'll go through this first one, and in this case I'm just saying that u is going to be the natural log of x, and dv will be the rest of the integral, which is an x to the fourth dx. Note that your dv always will include the dx because it's a differential. So the u is some part of the integral, then the dv is something involving the dx. Now if we have u and dv, we need to find du, which is just a regular derivative. So I take the derivative of natural log of x, I get a 1 over x, and then dx for my differential. And then the dv, in order to get v, I just have to do an antiderivative. So my antiderivative here would be a 1/5 x to the 5th. Right? And then I put all these together to create our new integral. So I'm going to have first uv. If I multiply the u and the v together, I've got 1/5 x to the 5th times the natural log of x minus my super voodoo, so integral of v du, so that's a 1/5 x to the 5th times 1 over x dx. Notice that that dx from the du became the new dx for our new integral. So once we've applied integration by parts here, we have one piece that's not in an integral, so I really don't care about this piece. That can be anything. And then the second piece, this one reduces, right? So I can cancel an x, and I end up with the integral of 1/5 x to the 4th dx. Now in this case, this was a successful application of integration by parts because we do know how to integrate this piece here, whereas of course we did not know how to integrate the original integral. So my last step would be to do that integral, which in this case was just a reverse power rule, and then that's my answer. You could check the answer here by taking the derivative of this and showing that we get back the original. That would involve doing a product rule on this first piece, so that's that kind of reverse product rule piece. So when you do integration by parts, you have to be able to choose what part of your integral will be the u and what part will be the dv. And there's some different ways to do this, but the main idea is that whatever dv is, we have to be able to integrate it. So often your dv is going to be kind of the largest or most complicated part of the integral that we can still integrate. So it can't be too complicated. We can't pick dv to just be, the whole integral, for example, or we wouldn't be able to integrate that. And then the u, we would like the u to get simpler when we take its derivative, although that's not necessary. But most of the time, if we have something in the integral like, say, an x, that's a good u because when you take the derivative, it gets simpler. There's also this acronym detail, which basically says that whatever you pick for dv should be these pieces in order of preference, I guess. So the first one is exponential, the second one is trig, the third is algebra, so that would be like powers of x and things like that. I is inverse trig, and L is logs. We almost never want logs to be in the dv because we don't actually know how to integrate a log. Remember, we know the derivative of a log, but not the antiderivative of a log. So you can use this one. This is not what I use for integration by parts, but it's a handy little tool. All right, so if we look at this problem, I've got an x sine x dx in the integral. So I want to think about what different possibilities we've got. So remember that dx has to be under the dv. So the first option we could do is to have u be the whole inside of the integral, and then dv just be dx. The next option we could have is one piece in each, so maybe an x and a sine x dx, or a sine x and then an x dx. And then the final option would just be to have sort of nothing in the u and have the whole thing in the dv. So those are all the possible options we have for u and dv. Now, one of these will not work right away, and that's this last one, because if we let dv be x sine x dx, we have to be able to do the antiderivative of that. And if we knew how to do that, we wouldn't be doing integration by parts, because that's just the original integral. This first one isn't really a good option either, because even though we can integrate dx, that's just integrating a 1, if we take the derivative of x sine x, it's going to be a product rule, it's going to get really complicated, and then that new integral we get is going to be a lot more complex. So that leaves us with the two middle ones. Now we can integrate sine x and we can integrate x, so that part with the dv is not a problem. So then looking at these two u's, I want to pick the one where the derivative of u is going to get simpler. So that would be this one. So let's try that. So I've got u equals x, dv equals sine x dx. So my antiderivative, the v part, will be a negative cosine x, and the derivative of u will be just a 1 dx. So we do our ultraviolet minus super voodoo. So ultraviolet is u times v, that's negative x cosine x, minus super voodoo, so that's a v du, that's a negative cosine x dx. You have to be really careful with negatives in integration by parts because of the subtraction in the middle. You often get a lot of negative signs floating around. But we've got a negative here, so I can make that positive. And we do know how to integrate cosine x dx, so we're good. And there's our answer. Alright, so in class I would have you guys try both of these. Obviously we're not in class here, but I would encourage you to pause the video right here and just take a few minutes, see if you can figure out what piece of these should be the U and what piece should be the DV, and can you get the integration by parts to work out. I will give you a hint here. This first one will work out better if we rewrite it with a negative power to begin with. Okay, pause. Alright, for this first one, we've got a couple different factors in here. I would be tempted to pick the x piece for the u. I'd go ahead and keep the 4 with it, although you can put the 4 into either piece since it's just a constant. The reason being that this will get simpler when I do the derivative. Now I do need to make sure that what is left, what's going into the dv, that I can actually still integrate that. But we can integrate this, so antiderivative here would be a negative e to the negative x. Remember, this is a u substitution there. And then du would be just 4 dx. So then I get ultraviolet minus super voodoo. We can integrate this. That's another u substitution, so here we go. And there's our answer. This one is fairly similar to the one we looked at before. I'd like to put the cosine x into the dv, because I know if I take the derivative of that piece, it's not going to get any easier, but I can integrate it. Then I'll have the whole x squared in my u. I do du, and then v, and then put it all together. So ultraviolet minus super voodoo. Okay, now when we get here, we end up with 2x sine x. That's actually the same integral we looked at up top, but with an extra 2 in it. This is also an integration by parts problem. So we actually have to do 2 integration by parts here. On the second one, I'm going to do u equals 2x and dv equals sine x dx. Now when you do this second integration by parts, you want to be really careful with the signs. So we had a subtraction out front. I'm going to put big brackets because we're going to replace this integral with 2 terms, and I have to remember that we're going to subtract both of them. So there's the uv minus integral v du, and then you just have to be really careful to keep the negative straight. And then at last, we can integrate that last cosine integral, and there we go. So as I mentioned in the post, I'm going to skip over the secant cubed. We'll do that one in class, and this next one as well. And I'll finish up the video with talking about the tabular method. So the tabular method is something you can use when you know that you're going to have to do integration by parts multiple times. So that one we just looked at, we had an x squared times either a sine or a cosine. And so we had to do integration by parts twice, first to get rid of the squared and then second to get rid of the x. This one here is very similar. Because I have an x cubed, I'm going to have to do integration by parts 3 times. Now, we can definitely do that, but it starts getting a little bit messy, especially with all the negatives floating around. So this is just a little trick to do integration by parts multiple times without having to write them all out. So what we do is we make a table with a u and a dv, and we put our normal u and dv just like if we were going to do a regular integration by parts. I'll leave the dx off just for convenience, but really there's a dx in that dv column. And then you want to go through the table and take the derivative in the u column until you get down to 0. And then in the dv column you're going to integrate until you match up with the 0. Okay, so those are all my antiderivatives. Remember, there's a u substitution in all of these because of the 2x. Okay, now our answer is actually going to begin with uv, which would be x cubed times 1/2 sine 2x. But then the next term is going to be the product of these two, but with a negative sign from the integration by parts. The next term will be the product of these, but then with 2 negative signs, so that one is a plus, and then this one is a minus. So the way you do this is you start with a plus, you alternate signs all the way down. There might be many, many rows here. You could do this as many times as you wanted. And then you take these products to get each term. So putting all this together, I've got a positive x cubed times 1/2 sine 2x, and then a negative 3x squared times negative 1/4 cosine 2x. So that one actually becomes positive. And then a positive 6x times negative 1/8 sine 2x. And then finally a negative 6 times 1/16 cosine 2x. And then throw on your plus c at the end. And there's the result. Now this is only helpful if you have to do it more than once, right? So 2, 3, 4, 7, whatever times. But this is kind of a shortcut method. I won't actually test you guys on the tabular method, but I wanted to show you just in case you needed to use this in another class in the future. Alright, that's it for this video. We will do those ones we skipped and probably some more practice in class tomorrow.